Hello, welcome to Astronautics for Exploit. This is Dr. Ayoshola Ogunlele. Deep space waste-to-propellant transformation, a strategy for achieving long-duration deep space missions and sustainable presence beyond the Earth. For several centuries, based on persistent curiosity from one generation to another to unravel the mysteries of the universe, humans have been eager to embark on this space voyage for the exploration of regions beyond Earth's orbit, encompassing interplanetary space and potentially extending into interstellar space, the space between stars. In preparation for the future manned deep space voyage, various robotic spacecraft have been launched into deep space to study planets, moons, asteroids, comets, and other celestial objects. To achieve this feat, powerful rockets were designed to overcome gravity and propel robotic spacecraft and various propulsion systems were developed to move spacecraft through space. To realize humans' ambitions of long duration deep space missions, establishment of a sustainable presence beyond Earth, live and work in space, waste-to-propellant transformation technologies is an essential step which is currently being researched. Launching each kilogram from Earth is very expensive. Transforming waste into usable resources will help to significantly reduce the amount of propellant launched from Earth and thereby lowering mission costs and increasing payload capacity. These space missions, for example Mars mission and beyond, require enormous amount of time and resources. Converting waste into propellant and other consumables is vital to support astronauts for extended periods away from Earth's resupply chain. This allows spacecraft to carry more equipment and reduce dependence on resupply missions. Presently, various strategies, initiatives, and approaches of this space waste to propellant have been developed. Examples are waste to gas conversion, waste to solid liquid propellant, biological approaches, and in-space resource extraction for propellant. The focus points are as follows: deep space waste to propellant transformation, benefits of deep space waste to propellant transformation, challenges of deep space waste to propellant transformation, and strategies and approaches of deep space waste to propellant transformation. Deep space waste to propellant transformation. The concept of converting waste materials into rocket fuel in this space is gaining traction as a way to enable more sustainable and cost-effective long-duration missions. The aim of this space waste to propellant transformation is to reduce reliance on Earth-based supplies and enhance self-sufficiency of these space missions. Made in space recycler is illustrated in this picture. This space waste to propellant fuel transformation holds significant promise for enabling future deep space missions. Continued research and development efforts are necessary in order to overcome technological hurdles and make initiative approach a reality. To address the challenges and reduce logistical burden of transporting resources from the Earth, scientists and engineers are actively researching methods to transform waste generated in space into useful resources, especially propellant fuel. Illustration of space trash is shown in this picture. Benefits of this space waste to propellant transformation. Examples of the benefits are as follows: reduction of launch mass and cost, enhanced deep space exploration capabilities, increased mission reliability and robustness, improved space sustainability and waste management, potential for economic development, greater spacecraft mobility and lifespan, and reduced environmental impact on Earth. NASA astronaut demonstrating how to pack trash in the International Space Station is shown in this picture. Reduced launch mass and cost is another benefit of waste to propellant transformation. By producing propellant in space from waste materials, the mass that needs to be launched from Earth is significantly reduced. This allows for either larger payloads to be delivered or for the use of smaller, less expensive launch vehicles. In-space propellant production will enable larger spacecraft and habitats to be transported to deep space destinations, such as Mars and beyond, expanding the scope and duration of missions. Mission concept of debris removal system is shown in this picture. Increased mission reliability and robustness. Having the capability to create propellant on demand minimizes reliance on Earth-based resupply, improving mission reliability and providing greater flexibility in mission planning. Instead of storing or jettisoning waste, converting it into a useful resource helps to address the issue of waste accumulation in space. This also aligns with principles of space sustainability, aiming for net zero debris proliferation, unnecessary environmental impact, and unsustainable resource use. Orbital Singer's commodity augmentation reactor is shown in this picture. The establishment of in-space propellant production infrastructure could foster a new space economy, creating opportunities for resource extraction, processing, and refueling services. Ready access to fuel in space allows spacecraft in order to undertake more complex maneuvers and extend their operational lifespan. Servicing of the Hubble Space Telescope is shown in this picture. Challenges of deep space waste-to-propellant transformation. Examples are waste stream variability and complexity, system design and miniaturization, power and infrastructure contamination and purity reliability and maintainability, and byproduct management. Concept of lunar recycle challenge is shown in this picture. Waste stream variability and complexity. These space waste streams are likely to be diverse, including everything from human waste and food packaging to discarded equipment and scientific experiment residues. Developing a single system capable of efficiently processing varied materials into usable propellant is a significant technical order. The resulting propellant needs to be pure and free of contaminants to avoid damaging spacecraft systems, ensuring a consistent and high level of purity of available waste input is difficult. The diagram here shows the recovered water from the trash and processes the gas effluent before releasing the gas to the cabin. Another challenge is the power and infrastructure. Conversion and storage systems require significant power, especially from solar or nuclear sources, and robust infrastructure capable of operating in high-speed environments. The processing systems will need to be compact, lightweight, and robust enough to operate in the harsh environment of space. Spaceport challenge winners are illustrated in this picture. The resulting propellant needs to be pure and free of contaminants to avoid damaging spacecraft systems, ensuring a consistent and high level of purity from a variable waste input, which is very difficult. These systems need to operate reliably over long periods without significant maintenance, as in situ repair capability in this space will be limited. The picture here illustrates an astronaut working near the International Space Station. Strategies and approaches of this space waste to propellant. Examples are waste to gas conversion, waste to solid liquid propellant, biological approaches, in-space resource extraction for propellant. Artist illustration of space junk is shown in this system. Waste to gas conversion, pyrolysis or gasification, involves heating waste materials in the absence or with limited oxygen to break them down into a mixture of gases known as syngas, synthetic gas. These syngas, rich in hydrogen and methane, can be used to generate electricity or further processed to create propellant. Steam reforming employs steam in combination with heat to break down waste into syngas, which can be converted into fuels like methane. Orbital syngas commodity augmentation recover reactor targets converting trash and human waste into useful gases like methane and hydrogen. Various recycling processes for transitioning to a circular economy in space is shown in this picture. Waste to solid liquid propellant, recycling space debris. Efforts are underway to develop technologies that can capture and recycle space debris, such as defunct satellites, rocket stages, into usable materials, including propellants. Advanced material processing. Researchers are investigating methods to process various waste streams, including food packaging, clothing, and human waste. Metal rod propellant. This is an approach that involves converting metallic space debris into metal rods, which can potentially be used as rocket fuel in electric propulsion systems. End of life and recycling system is shown in this picture. Biological approaches, microbial conversion, microorganisms such as algae and genetically modified yeast are being explored for their potential to convert waste, including human excrement, into usable resources like fuel, oxygen, and 3D printable plastics. Bioreactors. Utilizing bioreactors that leverage biological processes to break down waste and produce valuable byproducts like fuel is another area of active investigation. NASA astronaut Mike Fosun demonstrating how to pack trash in International Space Station is illustrated in this picture. In-space resource extraction for propellant, lunar and Martian resources. It focuses on extracting water and other elements from the lunar surface or Martian atmosphere to produce propellant locally. Asteroid mining. Asteroids are potential sources of water and other valuable resources, which can be processed to create propellant for deep space missions. Servicing of the Hubble Space Telescope is illustrated in this picture. For more information, contact Astronautic for Exploits. You've been listening to Deep Space Waste to Propellant Transformation, a strategy for achieving long-duration deep space missions and sustainable presence beyond the Earth by Dr. Ayanshola Ogundele, with the focus points: deep space waste to propellant transformation, benefits of deep space waste to propellant transformation, challenges of deep space waste to propellant transformation, strategies and approaches of deep space waste to propellant. Thank you.